All right, welcome. Let's do some volume problems for AP Calculus. Now this video is going to be all types of volume. It's going to be volume with disks, volume with washers, and volume with known cross sections. And so if you're looking for, specific examples of those things, I have them, and those are separate videos. This is just BC Homework 8.2. Okay, so I'm going to, if you're just trying to scan through here and find just the ones you want, just the disks, just the washers, just the cross sections, I'm going to make sure to clearly label the problem number I'm working at the top. Okay, so I'm going to start with, and I'm going to just, each time, I'm going to redraw the region that I'm rotating or building on, and I'm just going to do it each time. So R3 around the x-axis. Okay, and they're saying that, okay, this is the same R1, R2, R3 we worked on the area homework. This is y equals 1, x equals 1, x equals 0, y equals 0, y equals x squared, and y equals the square root of x. Okay, and I'm just going to kind of freely be assuming that you know what we're working on. So R3 around the x-axis is going to be this. Okay, you can see that. This is number 1. Okay, R3 around the x-axis, this is where the axis of rotation is touching the region entirely, so it's going to be a disk scenario. So I'm going to get myself a radius. I know that when it's disks, it's just the integral of pi r squared. Okay, so my radius is going to equal top minus bottom, y equals x squared minus y equals 0. Okay. So I'm going to say, okay, volume equals pi times the integral from 0 to 1, because that's x equals 0 and x equals 1, of r squared is going to be x squared squared, so x to the 4th, dx. Okay? And that's going to be pi times 1/5 x to the 5th as x runs from 0 to 1. Okay, well, we can do that. That's going to be pi times 1/5 minus 0, so it would be 1/5 of pi. That's number 1. Okay, the second one, actually pull this out here so I can just look at it to the side. Second one, R2 around the x-axis. I'll be able to do that. R2 is the one that's between the two curves, and so I'm going to go around the x-axis. I'm going to draw my x-axis. This region is not touching the axis of rotation entirely, so it's going to have some hollowness to it, meaning I need to use the washer technique. Okay, and so the washer technique, I need a big radius and a small radius. Okay. For the big radius, I go to the far edge of the region, and I reach all the way back to the axis of rotation, and I might call that A. Right? I don't like to call the large radius and the small radius large r and small r, because oftentimes these regions, they call them r. So we can't use that for radius. Okay, and then I'll call that B. Okay. Length A, radius A, is going to be top minus bottom. That's y equals square root x minus bottom is y equals 0. Okay. And length B is going to be y equals x squared minus y equals 0. Okay. Now we know that in a washer situation, volume is equal to pi times the integral of large radius squared minus small radius squared dx. Okay. And so that's going to be x minus x to the 4 So that's 1/2 x squared minus 1/5 x to the 5th. When I anti-differentiate, I'm going to plug in 0 and 1. I think I'm going to just end up with a half minus a fifth, which is 0.5 minus 0.2 is going to be 0.3. So it's going to be 3/10 of pi. Okay. And all right, that'll be far enough. Number 3, solid formed by rotating R1 around the x-axis. All right. And this is going to be my axis of rotation. So since it's not touching the axis of rotation entirely, I'm going to be using the washer method. Okay, the large radius here, I'm going to call that A and label it in red. Small radius, I'm going to call it in blue. Okay, A is top minus bottom is 1 minus 0. b is top minus bottom is square root of x minus 0. So I'm going to say, oops, wrong color. Volume is going to equal pi times the integral from 0 to 1 of large radius squared minus small radius squared dx. Okay, so this is pi times the integral from 0 to 1 of 1 minus x dx. I'm going to take an antiderivative. Plug in 1, plug in 0, and subtract. When I plug in 1, I'm going to get a half, because 1 minus half is a half. When I plug in 0, I get 0, so I'm going to get half of pi. Number 4. It's going to be rotate R1 around the y-axis. Okay. Well, I know that if I'm going to rotate around the y-axis, I need to get x in terms of y. So I'll do that eventually. But okay, I draw the axis, and I see that the axis is touching the region entirely. So this is going to be a disk scenario. And I'm going to go over here. Say, all right, my radius is going to be over here. And my radius, I can express that with right minus left. Well, if I've got y equals the square root of x, and I want to solve for x, I'll square both sides, and I'll get x equals y squared. So on the right, I have x equals y squared. And on the left, I have x equals 0, because that's the y-axis. And so I get r is y squared. Volume is going to be pi times the integral from y equals 0 up to y equals 1 of, well, r squared is y squared squared dy. And that's going to be, hold on, why am I tripping up on this? Oh, 1/5 y to the 5th multiplied by pi, letting y run from 0 to 1. I think I was thinking about the fact that this is the same volume as as number 1, and it should make sense as to why. But I was also thinking about how, I think maybe eventually, I think the next one we're going to rotate R3 around the line x equals 1, and it is not the same as rotating R3 around the x-axis, which can be a little confusing. But if you really think about it, it's, well, if you're confused about that, come talk to me about it, and I'd happily explain to you why it's not the same volume. Anyway, so pi times 1/5 y to the 5th. Okay, so pi times 1/5 minus 0. And that'll be a safe place to stop. Number 5, we're going to rotate R3 around x equals 1, which is a vertical line. Okay, so R3, it's about like that. X equals 1 is this vertical line. And so I'm going to say, okay, again, I'm touching the region entirely. So that's going to be a a disk scenario, pardon me. And that's going to be my radius. Okay, if this is y equals x squared, then x equals the square root of y. X would really be plus or minus the square root of y, but we're over here where x is already positive, right, because the y-axis was right here. So it's going to be the positive square root of y. Okay, and then my radius, right minus left, is x equals 1 minus x equals the square root of y. Okay. And then, volume is going to be pi times the integral from y equals 0 to y equals 1. That's y equals 0, and up here is y equals 1. And r squared, so 1 minus square root of y, dy. Okay, this, I've got to distribute this, and so maybe I'll do that off to the side in a different color. Be right around here. Okay. If I want to distribute this, start first. Outside and inside will both give me a negative square root of y, so I've got negative 2 square root of y plus y to the first. Now, I know because I need to anti-differentiate that, eventually I'm going to just write that as y to the 1/2 power. So pi times the integral from 0 to 1 of 1 minus 2y to the half plus y to the 1 dy. I'm going to anti-differentiate. Okay, add 1 to the power. Divide by the new power. So that would be 2 times 2/3 is going to be 4/3 plus 1/2 y squared as y runs from 0 to 1. Okay, and then I'm going to have pi times 1 minus 4/3 plus 1/2 minus when I plug in 0, all three of those will go to 0. Okay, and that's going to be a volume for me. And that was number 5. Number 6, we're going to rotate R1 around the line y equals -1. Okay, this is R equals 1. I mean R1, not R equals 1. And then y equals -1 is going to be all the way down here, not touching at all. So that's definitely going to require the washer method. Okay, so first I draw my large radius, going from the far side of the region that we're rotating with respect to the axis, right? So that's the farthest thing away. All the way down to the axis. And the small radius, we go, I think maybe in the past, I might have told people to start at the axis and reach to the near side. I think that's I've been going backwards. It's been a year since I've done these problems. A and B. And so I need to write down A and B in terms of x because I'm rotating around a horizontal axis. So A is equal to top minus bottom. Y equals 1 minus y equals -1. And then so that'll be 2. And then B is equal to y equals square root x minus y equals -1. Okay. So that's going to be, that's 2, and this is square root x plus 1. So the volume is going to be volume equals pi times the integral from x equals 0 to x equals 1 of a squared minus b squared. So that's 2 squared minus square root x plus 1 squared dx. Okay, this one, I think that some of these, just in the interest of time and me being able to record this video and do other things with my day, some of these I'm going to do with a calculator, and this is one of them. Not that it would be really that difficult. It would just be very similar to the last one where I need to square this thing. It just have a lot going on. So what I'm going to do is I'm going to just do this one with the calculator. Oftentimes these problems allow the use of a calculator. All of these problems can be solved without the use of one. That may be a lie. At least all of the ones on this page, 1 through 13. They can be solved by hand, but I think just, to save myself some time, I'm going to do this one and maybe a couple others with the calculator. Okay, and I get 3.665. Always 3 decimals. Okay, so number 7, rotate R2 around x equals -2. All right, well, R2 is the one that looks like that. And let's get all the rest of that out of the way. And we're going to rotate around the line x equals -2, which is a vertical line that's all the way to the left of the y-axis, and so it's not touching the region at all. So I need to get a large radius and a small radius. I'll get the large radius by starting at the axis of rotation and reaching all the way to the far edge of the region. That's definitely how I used to tell people to do this. And then for the small radius, you start at the axis of rotation and reach to the near side of the region you're rotating. Okay. Then, because we're rotating around a vertical axis, I need A and B to be expressed in terms of y. Okay. So we've already done this once, so I'm going to say this was y equals x squared, so x equals square root y. And this was y equals square root of x, so that's x equals y squared. Okay. So A is right minus left, x equals square root of y minus x equals -2. And that's going to be square root of y plus 2. So I can get that in there. And then b is going to be right minus left, x equals y squared minus x equals negative 2, which is going to be y squared plus 2. All right, volume is going to equal pi times the integral from y equals 0 up to y equals 1 of large radius squared minus small radius squared dy. Okay, this is another one that, that's just a lot of algebra, and, for the sake of time, I'm just going to bring in the calculator, say pi times the integral from y equals 0 up to y equals 1 of, have square root of y plus 2 squared minus y squared plus 2 squared dy. The reason I put the 2 in the front is just so I didn't have to worry about the 2 going underneath the radical. 5.131. Great. Solid form by rotating R3 around y equals 1. Yeah, I think I'm going to do this one with the calculator as well, so let's just go down to the bottom of the paper. All right, number 8. R3 is this one, and we're going to go around y equals 1, so that's this axis. So this is a washer scenario. The washers, I'm going to say, okay, this is the large radius, this is the small radius. A is going to be top minus bottom, so it's the difference in two y coordinates, so this is y equals 2 minus y equals 0. And B is also the difference in two y coordinates. It's going to be y equals 2 minus y equals x squared. We know that our volume is going to equal pi times the integral from x equals 0 to x equals 1 of large radius squared minus small radius squared dx. So I've got pi times the integral from 0 to 1 of 4 minus 2 minus x squared squared dx. Get 3.560. Okay, number 9 is the base of a solid is R3 and cross sections perpendicular to the x-axis are squares. Okay, so we're going to go over here. We're going to do R3. This is number 9, right? Okay. With this, if they say, okay, cross sections are perpendicular to the x-axis, I draw something that's perpendicular to the x-axis. Okay, and then the cross sections themselves are squares, so the area of a square is equal to base squared. So that means that this is the base. The height would, come up over that. And I'm not going to try to draw you a picture of what this thing looks like because it's not a common shape. Okay, and so I'm going to say A equals base squared. Base is equal to top minus bottom. That's y equals x squared minus y equals 0. And so area is equal to x squared squared, which is going to be x to the 4. Okay, the area of a given cross-section square. And then we also know that volume is equal to the integral of area with respect to, well, really whatever axis we're cutting cross-sections perpendicular to. So it's going to be dx as x runs from 0 to 1. Okay. And that area formula is going to be x to the 4 dx. And, okay, that'll be 1/5 x to the 5th as x runs from 0 to 1. And that's just equal to 1/5. Number 10 is the base is R2. Cross sections perpendicular to the x-axis are semicircles. Okay, we'll do that. Okay, that's R2. Cross sections perpendicular to the x-axis are semicircles, so I cut perpendicular to the x-axis. This one's not entirely a croissant, but it's close to a croissant. Right, there's like little semicircles above there. Regardless, I'm going to just say that the area of a semicircle is equal to 1/2 of pi r squared. Now, if this is the semicircle, and I'm sure we talked about this in class as well, then top minus bottom is actually the diameter of that semicircle. The radius would be half of that vertical distance. So the radius is equal to half of top minus bottom. So half of y equals square root x minus y equals, minus y equals x squared. Okay. And so my area formula is equal to pi divided by 2 times radius squared. Okay. We know that volume is equal to the integral of the area formula. We're cutting perpendicular to the x-axis, and x runs from 0 to 1. So that's going to be the integral from 0 to 1 of pi over 2 times, let's see, I made the classic error, and I'll be honest, I'm doing this before I've delivered the lessons on cross-sections, so I didn't put the 1/2 in there before squaring it. So what I'm going to do is I'm going to put that in like that, maybe extend these a little bit, and now, okay, now we're good. Caught it just in time. It's like I was saying, the radius is right here. It's just half of the vertical distance between the two curves. Okay. So it's square root x minus x squared divided by 2 squared dx. Okay. I'm going to save some time, use the calculator here. Although we could definitely do this by hand if we absolutely had to, I don't find this to be one that's super likely for us to need to do by hand. Okay. If I needed you to do one by hand that was semicircles, I'd probably find one that worked out a little bit better. So I'm going to say math 9 from 0 to 1. Okay. Fraction. I'm going to have a lot of fractions. Pi over 2 times, now I'm going to add another fraction, this thing divided by 2, so square root x minus x squared dx. Just like I wrote it. It is always so concerning to me when it does that, when it removes the parentheses, but I've got faith, and I'm pretty sure that's the right answer. 0.050. Okay. Number 11, bases are 1, so that's the one up here. Cross sections perpendicular to the x-axis are rectangles with height 3. This one should have been the first one. That's all right. Okay, that's a cross section perpendicular to the x-axis. Area of a rectangle is equal to base times height. Okay, in this case, this is the base. Base equals top minus bottom, 1 minus square root x. Height is equal to 3 because they said so. Okay. Oh, forgot I'm writing my full-blown area formula here. Area is base times height, so that's 3 times 1 minus square root x, which, if you wanted to, you could call that 3 minus 3 square root x's. Okay, we know that volume is the integral of area. In this case, dx is x runs from 0 to 1 because I'm cutting perpendicular to the x-axis. All right, and I've got 3 minus 3 square roots of x as my area formula. You know, I think this one is one that I'm going to be able to do by hand because it, you know, it looks like it'll be quick. So this will be 3x, that antiderivative, and the antiderivative of 3 times x to the 1/2 is I'm going to add 1 to the power. So it'll become x to the 3/2. And I will divide by the new power, which is like multiplying by 2/3, so I'll end up with a -2 there. And I'll let x run from 0 to 1. Wow. That's really nice, right? Because I now have 3 times 1 minus 2 times 1. And then when I plug in 0, I'd get 0. So this is going to be 1 unit of volume. Okay. That's nice. Okay, that was number 11. Now let's do some that are cross-sections perpendicular to the y-axis. Okay, number 12 is... Number 12 is base R1. So same region. Cross-sections perpendicular to the y-axis are isosceles right triangles. Okay. Isosceles right triangles are, I don't know if I went through in the lesson and gave you this, but an isosceles right triangle is, those are equal, and it's 1/2 base times height, so if this is base, that's also base, it's 1/2 base squared. So the area of an isosceles right triangle is 1/2 times b times b. And in this case, base is right minus left. So base is right is, this is y equals square root x, so x equals y squared minus x equals 0. And so my area formula is 1/2 of y squared squared. So that would be 1/2 of y to the 4th. Okay. The volume we know is equal to the integral of the area formula. The formula depends on y because our cross sections are perpendicular to the y-axis, and we're going to let y run from 0 to 1, which is 1/2 of y to the 4 dy. Okay. And this is going to be, okay, add 1 to the power, divide by the new power, so that would be 1/10 of y to the 5th as y runs from 0 to 1, and that'll be 1/10 of 1 minus 1/10 of 0, and that's just 1/10. Right. Number 13 is going to be base is R2. Cross sections perpendicular to the y-axis are equilateral triangles. Now, I'm not sure if this is really still, and like AP calculus, I haven't seen one of these in a long time, but you know, it's definitely possible. So, you know, if you had to go and investigate on the formula for the area of a equilateral triangle, I don't know if this was in the lesson, so I'll just go through it once right here. If you already know what the formula is, feel free to fast forward for me. This is the base. And then, oh yeah, so if it's a 60, 60, 60, half of it's going to be a 30, 60, 90. So this small one is base divided by 2, and that's the short leg of the 30, 60, 90. The long leg will be b times root 3 over 2, and then that will probably be just b, yeah, because it's equilateral. Okay, so this is b times root 3 over 2. And that's probably too small for you to even see, but whatever. Okay, and remember the area formula is 1/2 base times height. Okay, generally write that in green. Try to stick with that. Area formula is 1/2 times base times height. But that's 1/2 times base times height is root 3 over 2 times the base. And so I combine those and I get root 3 divided by 4 times base squared. Now I need to write base as a right minus left, right, because it's horizontal. On the right I have y equals x squared, so that's x equals square root of y. Minus, okay, on the left I've got y equals square root of x, so that's x equals y squared. And so now finally my area formula is going to be root 3 over 4 times square root y minus y squared squared. Okay. Now the volume is equal to the integral of area, cutting with respect to y from 0 to 1. And so that will be the integral from 0 to 1 of root 3 divided by 4 times square root y minus y squared squared dy. So I'm going to go over here, and I'm going to just make that happen. I'm going to factor out the root 3 over 4. Root 3 divided by 4 multiplied by the integral from 0 up to 1 of square root of y minus y squared squared dy. I get 0.556. Okay, and that was, those 13 problems in and of themselves were a good exercise in all three types of volume problems. But, I got 2 more pages. All right. Okay, now number 14, we're going to find the area and then the perimeter and then a volume. Okay, so the area of G, what we're going to do is we're going to take top minus bottom. Okay. So it's going to be the integral from x equals 0 to x equals pi over 4 of top is secant squared x, bottom is sine of 4x. Okay, couldn't see that. That's what I wrote down. And I'm going to do this one by hand because, we can. Okay, we know an antiderivative for secant squared x, a function whose derivative is secant squared x would be tangent x. Minus, an antiderivative for sine would be negative cosine. So I'm going to say, my hypothesis would be cosine of 4x. That would be, its derivative would be negative sine of 4x times 4 for the chain rule, so I divide by 4. And I let x run from 0 to pi over 4. Okay. So now what I'm starting with is tangent of pi over 4. Okay. Over here at pi over 4, this is 1 over the square root of 2. That's also 1 over the square root of 2. That's 1. So tangent would be 1 because it's 45, 45, 90 triangle. So 1 plus 1/4 of the cosine of pi. Okay, pi is over here on the unit circle. Its x-coordinate is -1. Okay, so that's when I plug in pi over 4 minus tangent of 0. Okay, 0 is over here. It's y over x. Y is 0 and x is 1, so that's going to be 0 divided by 1 plus 1/4 of the cosine of 0. Cosine of 0 is the x-coordinate right there, and that's going to be 1. So that would be 1. And then that would be a safe place to stop. Okay. And so, so it's a half. Interesting. Okay, find the perimeter of G. Well, oh my. All right, well, the perimeter of G, we're going to need, all right, it's going to be 1 plus secant squared pi over 4 will be the height there. So 1 plus, all right, at pi over 4, this is root 2 over 2, and that's 1. So cosine of, I'm going to actually just use this space over here. Okay, we've got this. That means that secant of pi over 4 is equal to 2 divided by the square root of 2. And secant squared of pi over 4 is going to be 2 over root 2 squared. So that would be 4 divided by 2 is going to be 2. Okay. And so I know that, see that now it's got a height of 2. Okay, so I've got 1 plus 2 plus, the integral that represents the arc length of y equals secant squared x. 1 plus, all right, derivative of secant squared x would be 2 times secant x to the first times the derivative of secant x, which is going to be secant tangent. Okay. Plus then an integral for, let's see, the bottom curve, 1 plus, the derivative of sine of 4x would be 4 cosine of 4x. We're going to square that, throw it inside a square root, and integrate it with respect to x. Okay, that's a lot. Okay. No, I think I'm just going to say that you could put that in the calculator. We could put secant x into the calculator by using the fraction bar on 1 over cosine x. And you could do this with a calculator if you needed. You couldn't do it by hand, barring some sort of really unexpected trig substitution that I'm not seeing right now. But besides, trig substitution not a part of the class, so we don't have to worry about it. Find the volume of the solid formed by rotating g around the horizontal line y equals -3. Well, I'm going to just kind of replicate the region here. Y equals -3 will be down here, so I'll need a large radius and a small radius. The large radius, I'll start at the axis of rotation and reach all the way to the far side of the region I'm rotating. And for the small radius, I'll start from the axis and reach to the near side. Okay. A is going to be equal to top minus bottom, secant squared x minus 0. B is going to be top minus bottom, sine of 4x minus 0. And then that means that the volume is going to be pi times the integral from x equals 0 to x equals pi over 4 of top squared, large radius squared minus small radius squared. I believe secant to the 4th power is the type of thing that we don't have an antiderivative for, so you would need to run this through the calculator anyway. And so in the interest of time, I'm going to say, I think I trust you to do that yourself, and I'm not going to do that in this video. Okay, G is the base of a solid. Cross-sections of the solid perpendicular to the x-axis are semicircles with diameter in region G. Find the volume of the solid. Okay, so I'm going to do the same thing. I'm going to kind of draw my replica. Cross-sections perpendicular to the x-axis, I draw one of those. Okay. Area of a semicircle is 1/2 pi radius squared. Radius is half of this length, so radius equals half of top minus bottom. Okay. So my area formula, if I had room to write it, it would be 1/2 pi times this whole thing squared, including squaring the half. So what I'm going to do, this is another one that I'm just going to set it up and not evaluate it. That would be 1/2 pi radius squared. Okay, to write the radius, I'm going to divide the whole thing by 2. Secant squared x minus sine of 4x. Okay, and then that's what we're going to integrate with respect to x. It's another situation where you don't want to do this algebraically by hand, because then you get to the point where you go to take the antiderivative and not going to be possible. So you got to use a calculator anyway, and again, I think you can do that. All right. Region N is bounded by the graphs of y equals 2 to the x, y equals 4 to the x, and x equals 1 as shown in the figure. Okay, find the area of N. Find the perimeter of N. Find the volume of the solid in N around the horizontal line y equals 4. And it sounds like I've got a class about to come in, so I'm going to have to pick this up in a few minutes.
Where's the 4 and the 6 coming?
Okay, so the area of N is going to be integral from x equals 0 to x equals 1 bottom. I'm going to run that with a calculator. Although these are technically integrals you're supposed to be able to run in this class. I didn't talk a whole lot about it. Probably just touch on that right before we review for the exam. Odds of that actually happening on your exam are pretty minuscule, so I think we're good for now. Integral from 0 to 1 of 4 to the x minus 2 to the x dx is going to be that 0.721. All right, find the perimeter of N. Well, this vertical length will be the difference in 4 to the 1 and 2 to the 1. So it would be 4 minus 2 is 2 plus the integral from 0 to 1 of the square root of 1 plus the derivative of 4 to the x is 4 to the x times natural log of 4. And then I'll do the same thing for the lower curve. So integrate 0 to 1, the square root of 1 plus the derivative of 2 to the x is 2 to the x times natural log of 2. We'd square that. Okay, I've been skipping a bunch of these, so I will show you. It looked like we did this with the calculator. Okay, I can sneak that in there. 2 plus the integral from 0 to 1 of the square root of 1 plus 4 to the x times log of 4 squared dx plus integral from 0 to 1 of the square root 1 plus 2 to the x times natural log of 2 squared, and it's going to get 6.607. Okay, rotating that around the line y equals 4. Maybe I'll sketch on the figure here. Okay, so that's my axis of rotation. Okay, I'm going to start at the axis, and I'm going to reach to the far edge of the region I'm rotating. That'll be my large radius. I'll start from the axis of rotation and reach to the near side of the region I'm rotating. That'll be my small radius. A is top minus bottom. A equals y equals 4 minus y equals 2 to the x. And B is going to be y equals 4 minus y equals 2. No, I did that wrong. That's what, and that is exactly why I like to draw the things. Okay, this is 4 to the x, so B is 4 minus 4 to the x. Just need the eraser. It is the exact reason why I draw those. So this would be 4 to the x, and A is going to be 4 minus 2 to the x. Okay. Find the volume of the solid formed by rotating in around it. Okay, so we know that volume is going to be pi times the integral from, in this case, x equals 0 to x equals 1, large radius squared minus small radius squared dx. And that's something that I would trust you to run through the calculator, but I'm not going to have time to do that right now. Okay. Region N is the base of a solid. Cross sections perpendicular to the x-axis are squares. Find the volume of the solid. Okay, I'm going to reproduce the region. Okay. And perpendicular to the x-axis would look like that. They are squares. Area of a square is base squared. Base is top minus bottom, so that would be 4 to the x minus 2 to the x. We've got our volume formula. Volume for cross sections, as x runs from 0 to 1, is the integral of area. So I'm going to take B and I'm going to square it. Base squared. So 4 to the x minus 2 to the x squared. Then I'm going to get the calculator out, and I'm going to integrate from 0 up to 1 on 4 to the x minus 2 to the x squared. That's going to be 0.842. Just a few more here. And the volume of the solid generated by rotating the region around the y-axis. The second one. Oh, okay, I see it. Okay, I get it now. I thought that one's going to require shells, and shells are not part of this class. But well, we can do that with washers. Yeah, definitely. All right, so rotate the region around the y-axis. Oh boy. Let's zoom in a couple more times. And I'm going to just solve for x on these because I know if I'm rotating around the y-axis, I'm going to have x as a function of y. So y minus 1, and then I'm going to multiply it by 4. So I'll get 4y minus 4 equals x minus 3 squared. So I'm going to take, this is going to be the square root. I guess it's plus or minus the square root. Oh man, this is rough. That's equal to x minus 3. And so when I add over the 3, it's going to be 3 minus the square root because it's places where x is less than 3. So That type of solving is beyond the typical AP calculus, what you would need. That's too bad that happened. It's a little tough, but, that's why you tune into the video. Yeah, I looked at my old key and I did it wrong. Was not, but yeah, it definitely is x equals 3 minus the square root of, because, how else would you get x equals 2 right here? 3 minus 1. So, it's all right. We're going to, what are we going to do? We're going to solve for this one. This will be much easier in contrast. So y minus 1 equals x squared, so x equals the square root of y minus 1. And x is positive, so I know that square root needs to be positive as well. Okay, and I think I can zoom out now. And so I'm going to say, crowded drawing here. My large radius, start at the axis of rotation, reach to the far side, call that A. A equals right minus left is going to be 3, x equals 3 minus the square root of 4y minus 4. And minus x equals 0 because it reaches all the way to the y-axis. And this smaller radius right here would be right minus left, would be x equals the square root of y minus 1 minus x equals 0. And just, again, in the interest of time, I'm not going to be running this through the calculator, but if you needed to, then you definitely could. I'm just going to set it up and not evaluate it. That's going to be the integral from y equals 1 to y equals 2 of, and since I defined these, is something you can do in free response that I'm really advertising, but if I am very explicit about what a and b equal and a and b are not already committed to something else, some other meaning in the context of the problem, I can say this is pi times the integral from 1 to 2 of a squared minus b squared dy, and that would be good enough. But only if I've really explicitly defined a and b. Here, I'm going to have to solve for x as a function of y here, and I think this will be a little better. So I'm going to have y minus 1 squared is equal to 2 minus x, so this would be x equals 2 minus y minus 1 squared. And that's this one. Then this one would be y minus 1 squared. And that would be that one. Okay. Now I've got large radius, small radius. Start from the axis, reach all the way across. Start at the axis, reach to the near side. And here, a equals right minus left is 2 minus y minus 1 squared minus x equals 0. And b is going to be y minus 1 squared. Okay. And then I'm going to get my volume is going to be the integral from y equals 1 to y equals 2 multiplied by pi and integrating large radius squared minus small radius squared dy. Okay. Shaded region is the base of a solid. Cross sections perpendicular to the y-axis are isosceles triangles with one leg in the shaded region. Basically, that just means that it's not the hypotenuse that's laying along the region perpendicular to y. Okay, so that's a cross section perpendicular to the y-axis. We know that the area of an isosceles right triangle is 1/2 times the base squared. And then the base is right here, because that's one of the legs. Base is right minus left. Well, I need to get that as x as a function of y. So I'll get x squared equals 3 minus y. And x equals the positive square root of 3 minus y, because we are over here in a region where x is positive. And so b is the square root of 3 minus y. Okay. The volume is equal to the integral of area. Okay, cross sections are perpendicular to the y-axis, so we'll be going from up to y equals, this is going to be 3 because y equals 3 minus x squared. Okay. And that's going to be 1/2 b squared is 3 minus y dy. Well, we can do that. You can even do this one with geometry if you really felt like it. But that's okay. I'll just do this one with fundamental theorem. So 3y would be 9 minus half of 9. And when I plug in 0, I would get 0 minus 0. And then there I'll have myself an amount of volume. I think it's 9 divided by 4, but you know. All right. Now, 25. The shaded region is the base of a solid. Cross sections perpendicular to the y-axis are equilateral triangles. Find the volume of the solid. All right, I already did one that was equilateral triangles, so I'm not going to go through the reason why the formula is what it is. I'm just going to say this is the base of the triangle. Area of an equilateral triangle is going to be root 3 divided by 4 times base squared. Okay. And base is equal to right minus left. If y equals 5x, x equals 1/5 of y. And so the base is, well, x equals 1/5 y minus x equals 0. So 1/5 of y. We know that volume equals the integral of area. In this case, dy is y runs from 5 to 10. And then I'll have, let's go back up here. Say this is the integral from 5 to 10 of root 3 over 4 multiplied by base squared. Okay, if I square that base, I'm going to get 1 over 25 y squared. And I might also say that's root 3 over 100 times, okay, now I'm going to take the antiderivative of just the y squared. I factored out the 25 just to deal with it a different time. And so it'll be 1/3 y to the third as y runs from 5 to 10. Ooh, do I know 5 to the third? Yeah, it's 125. Okay, 25 times 5. Okay, so root 3 divided by 100 multiplied by 1/3 of 1,000 minus 1/3 of 125. And that's going to be good enough for our purposes here. All right, now number 26, this one, again, I got you a nice good one at the end of the problem set to really challenge you if you felt like, this problem set was just not enough for you. If you felt like that was enough, then you just go be satisfied. This is well beyond the level of an AP Calculus volume problem, but it is a really good one to think about. And what I'll tell you, I'm not going to work that on this video. If you're interested but you don't know really what to do, my hint would be it's not a volume of rotation. You kind of got to set it up as a sections problem. And then you're going to have to figure out, like, what's the radius of those circles? How can I express the radius of those circles? And, it's a pretty challenging problem, but it's not something that you couldn't be able to do. So if you're interested, I'm going to ask you to come talk to me about it. But if you're not and you're satisfied with this problem set, which I got to think you would be, there's a lot of volume on that. If you're not satisfied, try it, come talk to me about it. Thanks for watching.